I want to introduce Denis. He's a professor in our psychology program, and I'm very grateful to him for doing this session. We've been talking about it since June, and I'm really excited about it and appreciate that you all are interested in the topic as well. So thank you very much.
Thank you. Thank you, Amy, for organizing this talk, and thank you all for coming. This talk is not about statistics. It's about science, because we're all scientists here, yet we all use statistics. So what I've noticed in teaching stats to psychology students, communication majors, biology students, is that there's often a disconnect between statistics and science. Students are taught a whole bunch of statistical methods, but they're not quite sure how they relate to the scientific practice. So the purpose of today's talk is I want to run through about 10 things to look for in a research paper to see if there's anything there, or to see if it's maybe just a statistical smokescreen. So what I'm presenting today is not something that is extremely complicated, but it's something that you want to look for in a research paper to see if the goods are there. Okay. So what are the top 10 things? We won't get through all of them, and some of them we might discuss quite extensively, but what are they? Well, first of all, does the tested model make sense? Now, you might look at that and you may say, well, obviously that's one of them. Why are you bringing that up? And the reason I'm bringing it up is because often we look at research papers where the model just doesn't make sense. Parts of the model may make sense, but other parts should not even belong in the model. That's fine, you say. Just focus on the parts you like of the model and ignore the rest. Well, it doesn't work that way in modeling, because you could have a beautiful statistical model, and then we all know you throw in another predictor, and all of a sudden it's like being on the raft in the summertime when you're all seated on the raft in the water, and then somebody comes on, sits on the raft, and people bounce off. The whole statistical model can shift a little bit. It might not, but the potentiality is there. So we have to be aware of this when interpreting models. What we call that in the modeling business is what? Model specification. Is the model specified correctly? Because if it's specified wrongly, even a part of it, it can throw everything off. Let me just give you my take on how I perceive models and how I relate them to scientific practice. We can think of model fit as an overlap of data and theory. Students start out by learning t-tests. They go to Anova, they go to regression, and then they get into maybe multivariate methods, and then they end up in structural equation modeling, where structural equation modeling, finally it's revealed that we're looking for a fit between data and theory. Well, if we start out with that premise, data and theory, the goal of statistical modeling, pretty much any model, is to see how well the two fit. Now, I've got an overlap up there, but what works really well is if you just use your hands and you go, look, good fit. As George Box once said, what do we know about the fit of models? Well, they could fit beautifully, but all models are wrong, right? All models are wrong. That's the first thing I like to tell my stat students, to deflate them real good for the rest of the course, that whatever model you come up with, it's going to be wrong. Even if the model fits really, really well, it's still never going to be perfect. But nonetheless, we're looking for that fit. I love airplanes. So, of course, I look at the model airplane as the perfect model. We've got the model airplane. We're trying to approximate the population airplane that sits on the runway. Parameters of the particular population airplane that we want to estimate with the sample airplane. Well, maybe there's wing speed, lift, and a whole bunch of things that I know nothing about. But nonetheless, we have our sample model. We have statistics on that sample model, and we use those statistics as estimators to estimate what's really going on in the population. There's two things to modeling, really. There's estimation, and then there's the structural model. Well, if I look at the structural model, I can look at it and ask myself, how well is this representing what I wish to study in the population? And that we can loosely look at as the specification of the model. But then there's the estimation of components of the model. So when I compute a statistic on the model, I'm using that statistic usually as an estimator of the population value. We do not care about statistics. That's another thing I like to tell my stat students is the book shouldn't be called statistics. It should be called parameters. Okay, we care about parameters. Why don't we study parameters? Too expensive. Populations are too big, so we settle for studying statistics. Use them as estimators of the parameters. But realize that whenever you look at a statistic, whether it's the sample mean, whether it's the sample variance, or a whole bunch of other things, we're really not interested in those things. What we really want to know are the parameters. It's a good thing to keep in mind. Understanding Anova and regression is the gateway to understanding many advanced statistical models. So Anova and regression pretty much do the same thing, but go about things a bit differently. Nonetheless, a good grounding in those two approaches makes other things seem much easier and kind of demystifies them. I like demystifying things. When I look at a multi-level model, for instance, random coefficient model, mixed modeling, at first they can seem very, very sophisticated until you look at them a little bit deeper and you just realize that, oh, it's just really an extension of the basic grounding in Anova and regression theory. All statistical models that predict a response have a random component associated with them, E, which is theoretically made up of an infinite number of things, one of which might be called chance, if you're so inclined to believe. If you're that religious that you believe in chance, go ahead. Some people might think that chance doesn't exist, so what is the error term made up of? Well, we can say that the error term is made up of all those things that are not included in the model, that have an effect, put effect in quotes because that's really important, have some kind of effect on that response variable. So if we look at the ideal scientific model, it would be nice if we can say y equals x, or x plus 3, or x plus other functions as well. That's OK. But the realistic statistical model is that it's y equals x plus e. And this is the joke that everybody likes to say. E is one researcher's error term, another's career. There's actually more to that joke than it seems, because I actually sometimes ask my students that by the end of the course. I tell them that joke, and the ones who laugh, I know get it. They got the course. The ones who don't figure, OK, you need a little more studying to understand what this means. Okay? So a whole bunch of people out there trying to break up that error term. Somebody comes up with a randomized block design. Try to get at the error term, try to piece it apart. Somebody in a regression approach tries to put in another predictor, partial out that predictor, or heaven forbid, control for the predictor. Control is something we're going to talk about as well. Well, there's the analysis of variance model. There's the ideal situation. I always like to start off with the ideal and then see how much I fall from the ideal. So that would be a nice idea if we had 4 different teachers. We were measuring, say, achievement data on them. And if the data came out like that, we would have trouble constructing our f-test, but that's a nice setup. No within variation, between group variation. We can see that there's an effect. We don't need statistics to address this. We can see there's something going on. If I look at the less ideal situation, well, there I have a bit of a mess. And I have that within group variation, and I still have the between group variation. So what does analysis of variance actually do? Well, analysis of variance asks the question, fundamentally, why are scores the way they are? And I think that's a good starting point to understanding modeling. So if I look at this, I literally want to know, why is 70 the way 70 is? Why is 67 the way 67? Why isn't it something else? So what do? Well, we try to theorize as to why the scores are the way they are. And this is the start of building the model. So I look at 70, and I say, well, 70, what could it be a function of? Well, they all receive the same teacher. Let me put that slide back up. They all receive the same teacher, so it can't be because they had different teachers as to why this person got 70. But this one's 70, this one's 67, this one's 65. So there's some unexplainable variability going on within the group. And I know most of you already know that. I'm just reviewing this to get the feel for, get us into talking about models and things. But there's that within group variability that's unaccounted for. When we bring in other predictors, other factors into the model, it's essentially to get at that within group chance variability so as to get a better prediction on y. So we can use, in ANOVA theory, we can use identities such as this one, which is the breakup of the sums of squares. So I have y sub I j, individual I in group j, minus the grand mean, is equal to the within plus the between deviations. We know that if I sum those up, I'm not going to get a very nice number. I'm going to get 0, so we're going to square the deviations, which leads to the partition of the sums of squares. SS total is equal to SS between plus SS within. There's the arithmetic of ANOVA, and our theory is that a given observation in a given group is equal to the grand mean, so the overall mean, plus the effect, there's my treatment effect of being in a particular group versus another group, plus the error component. Okay. So there's our ANOVA model, and there's the summary table for ANOVA. A couple comments on the summary table for ANOVA. Again, this is all falling under the umbrella of is the model specified correctly. So we're just reviewing a few modeling principles. So when you look at the research paper, you can say, well, do I trust the model? Is it reasonable? Here's our sums of squares between, within, total. We have our degrees of freedom. Now, one thing, you can get a lot of information from this table. One thing to realize is you can think of this as the descriptive part of the ANOVA table. And then once we go over the bridge of the degrees of freedom, I like to call it, once we go over the degrees of freedom, we get the mean squares, and that's where we get into inference. So there's a reason why when we talk about eta squared in ANOVA, we are not taking MS between over MS total. We are taking SS between over SS total to give us our measure of effect size. And that's another thing I want to talk about is the difference between effect size and the p-value, because that is extremely, extremely important. We get our F ratio, and what's the question we ask on F? What's the probability of U? What's the probability of getting an F like this? Again, I'm not talking too formally, but it's just to get the sense across. What's the probability of getting an F like that? If it was born out of a distribution on j minus 1 and n minus j degrees of freedom. Why do we want it to be less than 0.05? Well, 0.05 is completely arbitrary, but why do we want the probability to be low? Because if we get an F that falls off into the tail of the distribution, that means Fs like that don't happen very often under the null hypothesis of equal means, equal population means. So there's the classic ANOVA table, which we can adjust for regression problems as well. One thing to keep in mind, when you are looking at the research report, you want to know if the factors are specified as fixed or random. What's a fixed effect? What's a fixed factor? Well, if I look at my table again, and I'm only interested in comparing the means of teacher 1 versus 2 versus 3 versus 4. Those are the only 4 teachers I like to study, and I want to make conclusions about, then teacher is a fixed effect. So I'm only allowed to make mean comparisons. Now, would this be a fixed effect, or would it most likely be a random effect? Well, if I'm interested in the achievement scores for different students across different teachers, I'm probably not interested in just those 4 teachers. More likely, I'm probably interested in a population of teachers. So where teacher becomes a random effect is if I actually randomly sample teachers for the study. So theoretically, if I go into a bin of teachers and I pull out 4 out of a population, that becomes random. What's the advantage of treating it as a random effect? Well, the advantage is that if I find differences, variance explained between teachers, I can say that that's true about my sample data and teachers in the population as well. Okay. So you want to look for in the research paper whether the effect is fixed or random, because that's going to have huge implications. It's going to have implications for how the F ratios are constructed, but most importantly, it's going to have implications for what the conclusions are in the discussion section. More times than not, what we see in result sections and discussion sections is people start off with the fixed effects model, so they only say they're going to talk about these 4 teachers, and then what's in the discussion? They say, therefore, there's different amounts of achievement for different teachers. Well, that's not true. There's different amounts of achievement for these particular teachers if it was specified as a fixed effect. So that's important to see if it's fixed or random. Models are context dependent. Okay, and I talked about this just a little bit a while ago. It's saying that, what do I mean by context? I mean that if you have the model, it matters what predictors are in the vicinity of the model. So model 1, A predicts B. Okay, so we find a statistically significant regression effect, et cetera. Model 2, A does not predict B, given the context of C. So what happened? Well, first I had a prediction, and then I put in C. Oh, prediction's gone. So what's going on? Well, what's going on is just the partition of variability. But this becomes really hard to understand and really hard to explain to a biologist that, something had an effect, but if you put in another variable into the statistical model, all of a sudden the effect disappears, and we know that psychologists love that, because what's the second model? Mediation. Right? If you put in that other variable, well, the prediction disappears, then we can say mediation. Well, maybe we can say statistical mediation, but a little bit harder to talk about substantive mediation unless you have an argument outside of the statistical model. So that becomes a little bit tricky, and I'll talk about this more. You can't just look at a statistical model and say, hey, I got statistical mediation, therefore, hey, I've got a physical process going on there. X is pushing Y around, and Z is interfering like a mediator and going, you go there, you go there. You have to have the physical base for doing that. You can't just rely on the statistical model. What's the ideal model? Well, A predicts B given the context of the universe. I guess that's the best model. So does that mean controlling for the universe? Or does that mean ignoring the universe? I don't know. I don't know. That's kind of beyond my ability to know. But if you have all the variables in the universe and you're looking at the regression in question, that's the ideal model, because then you know that you've accounted for everything else that could be acting on that relationship. I often like to ask students, if you correlate height and weight, is that the true correlation between height and weight? So if I bring it to the media, I say if Anderson Cooper on CNN asked you, is X correlated with Y? What would you say? You'd say yes. But then if you put in other variables, you see the change in correlation. So what's the right answer for Anderson Cooper? Do you tell them it's correlated, or do you tell them it's not? Well, you're going to have to go to saying, well, there's a zero-order correlation, but partial correlation is going to change, and you have to bring in all these things. What I'm getting at is the truth of what we're talking about is actually pretty hard to get at when you take it outside the statistical realm and think about what it actually means scientifically. What does it mean scientifically? And that's the harder part. When you change the model, you change parameter estimates, you change statistical effects, you may not be changing real effects. If I take a balm and I put it on the wound and I watch the wound heal, I don't care too much about what the statistical model is going to tell me because I know the wound is healing. So if somebody shows me a statistical model and says, if I put in another predictor, all of a sudden I'm not seeing that effect. I'm seeing some kind of mediational effect. Well, I still know that the balm is curing the wound. So I can interpret the statistical model, and I also have the reality-based phenomenon going on, and I could see how well they agree with one another. What's the problem with a lot of social research? A lot of social research isn't as clear as having a wound. You can't see the wound. You have to rely on constructs. So what I like to say is sometimes a lot of modeling in a lot of the social sciences is model dependent. Does self-esteem predict future success? Yes. Let's say, I don't know. And then you put in another variable, oh, there's a mediator. Well, how do you find that in reality? It's not like looking at the wound and saying, I can match it up with the wound. So what I'm saying is that if all statistical theory went out the window and we kind of gave up on it, we said, my God, what we've been talking about is complete BS, we still have recourse to the physical model in situations. In other situations, we're dependent on the statistical model, and we should be aware of that. So when we're looking at the research paper, ask yourself, are the effects statistical, and do they match something in reality? Statistical models, even if specified reasonably well, may not correspond to processes in reality. You are never, ever testing individual effects in the model, no matter how simple the model may be. T-tests are context-dependent, as are SEM models, as are simple correlations. So again, to reiterate, if I do a correlation between X and Y, your argument may be that the model is incorrectly specified. Why? Because I did not include another variable that would have an effect on that correlation. So it's fair to say that even the simplest models may not be correctly specified. You're always testing the model, and hence the interpretation of parameter estimates must be within the context of the model. My favorite thing, my students can attest to this, that I love to grade them bad on their tests is that if I give them a multiple regression model with x and z predicting y, and I ask them what the effect is of x predicting y, if they don't say given the presence of z, then they don't get the point. Because what are they doing if they just say x predicts y? They're interpreting the bivariate effect in a more multivariable setting, which we know from mediation, moderation, and all that, may not hold. So you have to know the context of the model. Watch out for research papers that make those conclusions. X predicts y, period. X does not predict y, period. X predicts y given the model that is being tested. Really, really important, no matter how simple the model may be. Polynomial possibilities. Again, we're still under number 1 of the heading of what to look for in a model, see if it's specified correctly, does the model make sense? And whether it makes sense fundamentally comes from your substantive expertise. So you're looking at it carefully, you're inspecting it first, because if it doesn't make sense, forget about all the jargon, the statistical jargon, because you can just kind of throw the paper aside. Polynomial possibilities. Most models assume linear relationships. I think it's very reasonable that a lot of models assume linear relationships, because I think it's really hard to get nonlinear relationships in a lot of fields. And if we can at least approximate something by a line, we're doing pretty good. But it's still worth investigating a little bit, looking at it a bit, saying, why are they assuming linear? Now, the classic example of nonlinear relationships where things really are linear is when you just have a certain selection of data points that happen to be a different curve. And then all of a sudden you press trend analysis in SPSS, and you go, oh, look, it's doing this. Well, that could just be sample fluctuation. I doubt you have a cubic relationship there. You're probably better off with just saying it's linear. That gets to the idea, too, that we can fit data points, we can fit lines and curves to data points beautifully and have all kinds of complex curves. But the goal of science is to summarize the data, knowing what we know about the background area of the research. So be aware of too complex of curves fit to data, and ask yourself, does this really apply? Is this really a sign relationship we're seeing here, or is it really some kind of linear relationship and they're capitalizing on chance? There's the Challenger data as an example of a nonlinear relationship. There's temperature of the O-rings. When the O-rings failed on the Space Shuttle Challenger, they found out that with the number of incidents that happened with the O-rings expanding, well, it's a function of temperature. So that if you have high temperatures, you might have more incidents. If you have low temperatures, you might have more incidents. Not a lot of data, but you can see why the Challenger exploded at low temperatures, launched at, I think it was 51 or 53 degrees, where there's a lot of failure. Chance of failure was relatively high. Pearson R, another thing you're looking at in the research report in terms of under the model, the general model. If you come across Pearson correlation coefficients, remember they capture linear relationships, so you're always looking for a plot. Okay? Always look for a plot. If I give you an R coefficient, and I just say R is equal to 0.60, well, what do you know? You don't know much until you look at the plot. Okay? Likewise, if I give you a correlation coefficient, say a small one, you say, this does not mean there's no relationship. It means it doesn't look like there's any linear relationship. There may be something really, really wicked going on in your data that this isn't going to capture, because if your data look like this, R, by the way it's defined, is going to try to do something like that, and it's going to give you a low number. So never accept the statement in a research report that there is no relationship simply because there is a low Pearson correlation coefficient, and always look for a plot. There's our Pearson R there. Okay, still under the topic of models. We will get to number 2, I promise. Multivariate models. Okay? So you're looking at the research report, and you're seeing that they tested a multivariate model. Well, is that good or bad? Are multivariate models worth it? Well, the first thing is that they only make sense if they make good scientific sense. This is something I like to stress a lot, because I often see this, it's not a competition, but the more sophisticated the discipline of statistics gets, the more the scientist feels as though they should be using these methods, and they really look good at job talks because they're doing latent variable modeling rather than ANOVA. But I think we need to ask ourselves, does the multivariate model make sense? If it doesn't make sense to use for the scientific problem, I don't think we should be using it. So I think we should beware of misleading rules of thumb. The classic one is MANOVA. Here's a rule of thumb for MANOVA that sometimes people like to give. Use MANOVA when you have more than a single response variable. That's absolutely false. Statistically, it's absolutely nice. And if you have correlation among the response variables, sure, go ahead. MANOVA will control your type 1 error rate and all these things. But as a scientist, what is that statement telling me? Use it when I have more than a single response variable. Even if they're continuous variables, does it make sense? So if I draw a function statement up here where I have my y variables here and my x variables here, if I put y1 and y2 in a model, I'm looking at a MANOVA model there. If I have a categorical predictor, so there's my x with, say, 3 levels, what's the justification for doing MANOVA? It's not that I have 2 variables. It's that these 2 variables, theoretically, according to my theory, generate a meaningful linear combination. And if they don't generate a meaningful linear combination, I shouldn't be doing multivariate analysis of variance. I'm probably better off with doing univariate analyses on each y. So if y1 plus y2 doesn't make sense theoretically, like if I'm studying self-esteem and how many times my dog barks, well, that's not going to make a lot of sense. So you want to make sure that they go together. So I think when we're looking at the research report, we want to see, okay, they did MANOVA. What's the variate? What's the dependent variate? What's the linear combination they're talking about? And if they're talking about a linear combination, a variate that you don't agree with, or you know the research area and you say, that doesn't make sense, that's a foolish linear combination, then MANOVA is the wrong strategy. Of course, if you are doing MANOVA, it has many statistical benefits. And one of the statistical benefits is it does capitalize on the correlation among variables. It could afford more power in some situations. And it'll help control your type 1 error rate. So instead of doing 2 univariate analyses, you just do this one, and you set your type 1 error rate at, say, 0.05, and you have control over it. But again, the statistical benefit should only come into play after the scientific benefit is accepted and realized. It doesn't make sense the other way. That's why I don't think it's right to say we do MANOVA because we have more than a single response and we want to control type 1 error. No, you do MANOVA because it makes sense. Oh, and here are the statistical benefits to doing it. I think that's important. We can say that when you perform a MANOVA, you're testing a different null hypothesis than when you perform separate univariate ANOVAs. And that just should not assume that the rejection of one hypothesis, the multivariate hypothesis, automatically informs you of the status of other hypotheses, univariate hypotheses. Likewise, you should not assume that individual univariate findings on separate response variables will necessarily generate a multivariate effect if combined. There's something known as Rayle's paradox in there, saying that you can reject multivariately, but fail to reject univariately, and vice versa can work as well. So we have to get out of this thinking of talking about the multivariate effect as decomposable into univariate effects. And again, how can we think about that? We think about if this is the correct model to test, then test it. If you follow up the model with univariate effects, those univariate effects should make sense from a theoretical point of view. You're not really chopping up the effect. One more note on multivariate models. Sometimes students look at multivariate stats and they go, oh my God, that's like a whole different thing. I don't want to take the course and I don't want to do multivariate methods. But really, there's a simple extension of the univariate models. So if we look at a t-test, and here's a t-test, independent samples group t-test, where we're subtracting constant of 0. So we're looking at a mean difference between two groups. Those are population means, but I'm taking the expected values, so they're really samples. There's my pooled variance down there, and I'm going to do my t-test. So we're all familiar with the t-test. Once I get into the multivariate domain, well, then I'm looking at the covariance among response variables. So there's my multivariate domain up here again, where as soon as I add another dependent variable, I'm looking at covariance between these. So if I take away this and I have two groups on this vector now, this is the vector. If I have two groups, well, then I'm into Hotelling's T. But look, Hotelling's T is actually very similar to univariate T. Here are my vector differences right here. That's the transpose. So I'm squaring it. That's all that is with this. And there's S to the -1, which is the inverse of the variance covariance matrix. What that really is just take these vectors and put this on the bottom in the denominator. And that's going to be an expression of variability and covariability, very much like this denominator is an expression of variance. So really, we're doing something a little bit different because we're getting the covariance between response variables, but really it's not that different than the univariate T. So when you're looking at the multivariate methods, always ground yourself in the univariate ones and just see them as extensions to it, extensions of the fundamentals. There's number one. So number one, does the model make sense? If it doesn't make sense, then the rest of the paper could be suspect. Number two, again, second thing you want to look for in a research report, is the design an experimental one or is it non-experimental? I tend to favor experimental designs. I know in a lot of survey research, I mean, there's no way of having the experimental design really. You need to gather data, correlate data. But I think that's one of the central things to look at. Is it experimental? Is it not? What are the consequences of it being one or the other? Statistical analyses can be used to analyze experimental or non-experimental data. Example, Anova is not experimental and regression is not correlational. Sometimes investigators think that if you're doing an experiment, well, then you should be doing Anova as the analytic process on there. But really, you can do regression just as well. Okay? The actual reason why Anova exists as a statistical methodology is largely for convenience. Regression came about in the 1890s or so, multiple regression. And had we had computers back then, this would have probably not arose. So it's computationally efficient. It was easy to partition. But had we computers in the 1890s, it wouldn't have had the same onset as it did in the 1920s. Anova was really big in the 1920s with R.A. Fisher. So the thing is when you're looking at it, at the research paper, if you see Anova, if you see regression, do not assume that one is experimental and one is correlational. You need to know the design, not just the statistical procedure. Second thing here is, does the word cause appear anywhere in the research? Does the word cause appear anywhere in the research? For me, at least, being a bit of a methodologist, when I see the word cause, I'm like, all right, I can't wait to read the rest of this to see what causes what. And I'm not even that philosophical. I hate to go to the philosopher and say, hey, I got a paper here that says that X causes Y. Care to analyze it? And I can just imagine what they're going to do with it. You're going to tear it up and go, where's the causation? First of all, what does the author mean by causation? Because we know that philosophers of science study causation repeatedly, and they still have trouble with understanding what is causation. How do you specify causation? So causation is really, really difficult. And I can't even explain it because I don't know what it is. So if somebody writes that in a research paper, I'm curious to see what their justification for it is. Does the word cause appear anywhere in the research? And if so, is it justified? That's the point I was just making. Now, one thing that we see in research papers is this idea of causal modeling. Well, what's causal modeling? I come down hard on this. I've looked at some of the history behind this, so I know a little bit of where this traces from. And when I see the word causal modeling, I just think of it kind of as a myth. It's kind of like the Sasquatch. It's like, that's not real. That's not real. It can't be causal modeling. Where does this come from? Well, if we look at the history, we see that the words causal modeling originated more or less in regression history, but more so in the history of path analysis. Wright was a geneticist who studied, among other things, guinea pigs, and he developed the procedure of path analysis, and he called the coefficients in the path analysis causal coefficients. They were path coefficients, and he called them causal. Well, that ignited a whole debate. And people were saying, well, you can't prove causation just because you choose to call the coefficient causal. Well, then Sewell Wright said, well, look, I'm working with guinea pigs. Okay? These are the guinea pigs. And he was interested in problems of heredity. Color of the guinea pig. If you mate the mama and the papa, what color does the little baby guinea pig come out to be? So in that sense, it wasn't a sin, methodologically speaking, to call those coefficients maybe causal coefficients. I mean, if you take the mommy and the pappy guinea pig and they mate, the baby guinea pig is going to be of a certain color. And I think it's reasonable to say that there's some kind of a causal effect that's producing the color in the baby guinea pig. So putting coefficients on these arrows towards the babies here could make some sense if you call them causal coefficients. But what happened after that? What happened after that is people started using this method of path coefficients and path analysis, and they brought it into their area of research. One of the first studies to use path analysis was one by Birks in 1928. And this one looked at parental intelligence and environment causing children's IQ. Well, there again, it was reasonable to put coefficients here and to maybe refer to them as causal coefficients and to call the whole thing a causal model. Why might it be reasonable? Well, maybe because that's the theory at the time, probably still is today pretty much. So we say parental intelligence, you have environment, nature, nurture debate. It made sense. But what happened after that was the economists, social scientists came around and they took this causal modeling methodology, and what happened with it was that all of a sudden you could have X, you could have Y, and you can say they're causing Z. But why doesn't that make sense? Well, you can put a beta coefficient here, you can put a beta coefficient here, but this is only going to make sense if what? It's only going to make sense if this makes sense, if it's a causal model. So you cannot take non-causal variables, throw them into a causal model, and then claim that X causes Z. It just doesn't make sense. So what can we say about this? We can say that before you use path analysis or causal modeling, which its overachieving offspring is structural equation modeling, that you have a causal context to the design before you start calling it a causal model. Otherwise, what is it? It's a regression model. It's prediction. So I think we should look for in research to see if they overstate the conclusions on the coefficients that they make. So I'd like to say that statistical model plus causal context equals causal modeling. Statistical model plus non-causal context equals non-causal modeling. Okay. Related to that, we'd like to look for, are there any directional or action statements used? And do authors justify why they're making such claims? Mediational or moderation hypotheses usually not confirmed by statistical tests. Moderation's a little bit more on solid ground because it's interactions. But mediation, there's lots of room for philosophical debate there. And we need to really be aware of this. I talked about it a bit earlier, that if I have my IV predicting the DV, or if the researcher might even say cause, again, look for the justification as to why they're saying cause. They can't say cause just because they're using a mediational model. When I throw in my mediator and this drops down, ideally to 0, well, what does that mean substantively? We can call it statistical mediation all we like, but substantively, what does it mean? And that's the harder part. So we need to be aware of that, I think. Was factor analysis, cluster analysis, or principal components used? I'm not going to talk very much about that, but were claims regarding their capabilities overstated? None of these procedures discover substantive factors or groupings. Oftentimes, we think of factor analysis as uncovering. Think of like uncovering something in the dirt and then going, the factor right there. But really, they don't. They don't uncover. They don't discover. They correlate. They correlate. So take a bunch of variables, correlate, reduce it down into components for principal components or factors in factor analysis, but there isn't any discovery, ontological discovery of any substance, just correlations put in a different way. Is the research statistically loaded but scientifically slim? Is the research merely a work of statistical art Example, numerous specification searches and lots of statistical jargon to make up for a weak scientific effect. What I think about that is sometimes researchers will test, it usually happens in structural equation modeling, where they'll test a model and then they run these specification searches on the model. They change parameter estimates. They fix, they free, they fix, they free, until the model produces a nice fit. And then, of course, that's when we say, hey, this thing's ready for publication. Get it in the paper, right? So is there a lot of that going on? Has the author been honest about how many times they ran their model? If they ran their model 1,000,000 times and are presenting the model that works, well, I think we need to be suspect about it. How theory-driven was the construction of their model, and how theory-driven was the estimation of the parameters that they chose to estimate. Number 3. Number 3 is a really, really big one. I don't know how much people know about this issue, but I really want to stress this. If you take away one thing about this talk today, I think this should be it, because it's really important. Are p-values and p-values alone used to justify a finding of sorts? Do researchers mistakenly equate p-values with effect size? The first thing is they're not the same. R.A. Fisher came up with the analysis of variance procedure in about 1925. A fellow by the name of Berkson, 1937, said, you know, the observant statistician actually realizes that they can get statistical significance if they just increase what? Sample size. If you just increase sample size, you can make p as small as you want, so long as there's some effect. If there's no effect, forget about it. It's not going to happen. But if there's some effect, just boosting your sample size will get you p is less than 0.05 or whatever number you want. Must be a problem with the significance test. No, the significance test is working just fine. It's doing its inferential job. In the math stats building, there's no problems with the significance test. In the science building, there is a problem, because when we look at the significance test and we try to conclude something about our research, that's where the bridge isn't that smooth. And methodologists have known this for years, and there's a whole litany of research on the p-value, problems with interpreting p-values, how to interpret them, problems of inferring things from p-values. Yet it still goes on where we see results in journals and things where we see p is less than 0.05, and that's somehow evidence for an effect. The medication is effective, p is less than 0.05. Well, scientifically, perhaps not that meaningful. Statistically, very interesting. Statistical significance is statistically interesting, but scientifically boring. It's just boring. So I don't mean to bring us down. But when we see this, the first question you should ask is, well, first observation you should make is, so what? If they're not giving you sample size coupled with this, you have no idea what's going on. What does this literally say? It means there's some difference in your sample means, to take the example of a t-test. There's something going on in your sample. Now, if I give you a sample size of, say, n equals 50, if I couple those two things together, then what do you start to think? Start to think, oh, maybe there is something going on, because probably the p-value isn't being deflated by simply the sample size. But of course, we can look at effect size. We can look at statistical significance in conjunction with one another. So we don't have to just arbitrarily guess at it. P is less than 0.05 is way overrated. P is less than 0.05 tells us the probability of some data given a hypothesis we already know is false before we were born. Do you get the point? I try to make the points I believe in very, very clear and kind of overstated. Everyone clear on why it's false? It's false because if I have two parameters, look, think of what the null hypothesis test. HO mu1 is equal to mu2. What a stupid hypothesis to test. We know it's false to begin with. You really think in the population for whatever you're measuring that the two population means are going to be equal? Not a chance. They're going to be unequal, and if they aren't unequal, carry a few decimal points and I guarantee you they'll be unequal. So already we know that when we look at this hypothesis, we know that it's going to be false. So problems abound with null hypothesis significance testing. The example of the medication is effective is a somewhat empty scientific statement, if not coupled with other information. And you can see, too, where if you're not aware of the influence of the p-value and the construction of it, it can be easy to get results by someone if they tend to believe that this by itself is valuable. Because you can just say, well, let's change the policy decision because I found an effect if p is less than 0.05. Well, if the receiver of that information has been taught that p is less than 0.05 equals good, well, then they're not going to know. Recipe for getting p is less than 0.05, adjust according to taste. This is just a few examples put up here. Well, there's a z-test for means. So we got our sample mean up here, minus a population mean under the null hypothesis right there. Well, look what's happening in the numerator. We have 20 minus 18. There's my distance between means of 2. There's my standard error. I'm using a z-test, so I'm pretending like we have the population standard deviation here. 2 divided by the square root of 16. 16 is my sample size. What do I get for my z-value? I get 4. Well, 4 is going to be statistically significant. But what if I want to boost it up? I could do it. Watch, I'm not going to change my effect. I'm not going to change my population standard deviation. I'm going to change my sample size from 16 to 49. What happened to z? Z increased to 6.9. What happens if I use a sample size of 100? We're not talking about big samples here. Sample size of 100, 10. If nothing else convinces you, the arithmetic of the z-test has to show you that just by increasing sample size for the same effect, you can get an increasingly large statistic, which means that the probability of this statistic is going to be a lot smaller than the probability of that one. So the p-value goes down as you increase the sample size. Now, one caveat. There's no saying what would happen to the population variance and my overall standard, or my standard deviation here if I increase sample size. The standard deviation could increase, it could decrease, we don't know. But holding these things constant, we see that the z, the t, and all other inferential statistics are a function in part of sample size. And there's the example with t, where look, in the numerator, I have a difference of 1. Difference of 1 point, yet I'm boosting my sample size. I got 2.2. I can go higher with a bigger sample size. So imagine if you're reading the research report, and the research report says, I found a difference in IQ levels between 2 groups. And they just report p is less than 0.05. They could be talking about this in terms of the difference, 101 versus 100. Yet if you're unaware of what the construction is of an inferential test statistic, you may come away thinking that you've just seen something that's meaningful, and even that could influence policy where you're saying, hey, we found IQ differences. You found a difference of 1 point. If I reduce this to even a smaller number, I can still get statistical significance as a function of n. So we need to be aware of it. P-values are OK. What do p-values tell you? They tell you that it looks like something might be going on in the population. You can reject this null hypothesis. But they do not tell you the magnitude of effect. They do not tell you what's going on. And unless you like looking at unless they show the statistics and you like looking at the construction, because we can construct effect sizes from this. If you look at it and say, OK, I see what's going on, then you're absolutely going to need an effect size to contextualize it. Same principle holds for f-tests in Anova and regression, as well as most other inferential tests. We cannot trust the p-value alone. Do claims such as the finding is highly significant appear in the research paper, and do researchers explain what they mean by this? Okay. That's just what comes to mind when I think, what does this mean? I just think of Frank Costanza giving it to George there, just yelling at him. So the finding is highly significant, but what does this mean? This is my favorite statement in a research report. X significantly predicts Y. Well, what does that mean? X significantly predicts Y. That's the first question. Does it mean you got p is less than 0.05? If that's what it means, then we know not to get too excited by that statement. Because if I look back at my t-test again, I see that I've got a difference in means Yet if I said something like x predicts y, or there's a statistically significant difference, I know I could be talking about a small difference. So in the context of, say, a regression, x significantly predicts y, that they could be talking about an r-squared of 0.003. Really, really small. But they found statistical significance for it due to the large sample size. So when we see a statement like that, I think that that statement, if the researchers are really, really honest about it, should reflect what? An effect, such as an r-squared, an eta squared, where you say, well, 30% of the variance is accounted for in y by x. X significantly predicts y. That's a great scientific statement. But as this stands, this is the statistical statement. It's not necessarily the scientific statement. Are the null hypotheses posited reasonable? Does a rejection of such a null impress you as a substantive expert? Did researchers infer the alternative of their liking based on data implausible to the null model? All null models can be rejected if they are juxtaposed to conflicting data. I think that's important as well, because when we look at the significance test, we're looking at the probability of data in light of a null hypothesis. So this is what we're looking at, probability of data given HO. Well, the probability of the data, as reflected in our statistic, that probability can be made as low as you want if you just specify the right null hypothesis that will get it so. Okay. So if the null is not reasonable to begin with, or even if you kind of doubt the validity of the null, it's not a good thing to subject to test, then all p-values that you observe are not really valid, and it could be somewhat of a smokescreen with a whole bunch of significance values, a whole bunch of stars. Statistical alternative does not equal the substantive alternative. Okay, they're not the same thing. What's the statistical alternative? The statistical alternative is an expression of not the null. So if I take the null hypothesis and I reject, I'm going to infer the statistical alternative, which is a statement of not the null. Doesn't look like the null is the model we should be adopting. But why isn't it equal to the substantive alternative? Well, what's the substantive alternative? The substantive alternative is why the null is rejected. So once you reject the null hypothesis, the substantive alternative is why. And why would you reject a null hypothesis? Well, hopefully you did something in your experiment that's going to generate the rejection of the null hypothesis, like treating one group differently than another group, so that when you reject the null, you infer the statistical alternative, but you can also say why it's happening. The hardest part, statistically, it's actually not that complicated because we just reject the null. But the scientific problem is the explanation. And how many competing explanations could there be for why you rejected the null? There could be an infinite number. Okay, there could be an infinite number of substantive explanations. But how do we control those substantive explanations? Through maybe experimental controls or design features. So that when we do reject the null, we say, OK, this must be why it's happening. And even then, of course, it's always going to be imperfect. But that gives us our best chance of isolating why this is happening. Okay. Did researchers call findings such as p is equal to 0.06 not significant and dismiss them as unimportant? The difference between p is equal to 0.049 versus p is equal to 0.051 practically means nothing. The 0.05 level, 0.05 was cited by R.A. Fisher, the inventor of Anova, as saying it's usual and convenient for researchers to take 0.05 at a level such that they're willing to ignore results that do not reach this level. He was talking about this mostly in the field of agriculture, and he said it was usual and convenient. He meant it as a guideline. He meant it as a guideline, not a gospel. It's not a gospel. What's happened, though, is people have taken the 0.05 level, and they've taken it as, they call it the cliff effect. Less than 0.05 is a good thing. Greater than 0.05 is somehow not good, like a bad thing. But scientifically, we only wish to see an unlikely statistic. We only want a low p-value under the null. The exact probability of the data under the null is usually scientifically irrelevant. Okay, if I had a mathematical statistician, I'd just be killed for that statement. I'd just be completely torn apart. And for good reason, because formally, what do we say in statistics? We say, well, put your null hypothesis, specify your rejection region, and if you specify your rejection region to be 0.05, then when your statistic comes out from your research, obey your decision criteria. Therefore, if the p-value is greater than 0.05, you don't reject. If it's less than 0.05, you do reject. There's the formal way to test your hypothesis, and I completely agree. I'm not meaning to cause problems. But I'm saying from a scientific point of view, what's the difference between those two numbers? There is no difference. I mean, there's difference numerically, but pragmatically, there's no difference because you're just looking for an unlikely statistic. So I think what's going to happen, somebody had an RSVP question about simulation in research, and not to comment on simulation right now, but I think what's going to happen more and more is because computers are just spitting out p-values, less and less are we going to be doing this formal idea of specifying a significance level, testing the hypothesis, and rejecting. We're just going to be looking at the p-value, and scientifically, what are we looking for? Say, oh, p is pretty low. It's getting in the ballpark. Hey, maybe something's up. Small p-value, let me look at my effect size, see if something is actually happening in the study. But this thing about decision versus not decision from a scientific point of view, it just doesn't make any sense. And also, why doesn't this, what's another reason why this is a little bit iffy? Well, this minimizes your type 1 error rate, minimizes the probability of falsely rejecting the null hypothesis, but what error rate does it not pay any attention to? The type 2 error rate. So my favorite example that I use with students is saying, you know, if there's a superbug out there that's killing people day in and day out, and you get the grant to see if you can develop the vaccine that'll save people, and you run your statistical test, and your statistical test comes out to be 0.05, well, let's say 0.06, are you going to report a finding? Sure you will. Why? Because the risk of a type 2 error is so high that if that vaccine is working, you want to get it out there to save people. So using this as an arbitrary level just doesn't make sense. Now, that's been going on for 80 years, 80, 90 years almost. And the problem is there's become a sociology of science where instead of trying to explain to an editor these differences, people just get it at 0.05 and then the manuscript gets accepted. If you publish up, say, 0.07, 0.08, you may face a little bit of an uphill battle by explaining to the editor the differences because he or she may not understand them. But I think it's really worth it in terms of bringing statistics into science and understanding the difference. Number 4, did researchers replace missing values? Did they delete outliers? I'm going to say something else here that a lot of people may disagree with. Replacing missing data is also known as making up data. Okay. Sorry. That's my opinion. I don't care what algorithm you're using. I don't care how sophisticated your missing data procedure is. I don't care how good of a job it does. When you put an observation into the cell that's not there, it's called making up the data point. Okay. You don't know what that observation would have been, but you're guessing on it, and maybe you're making a good guess by using the sophisticated algorithms that some statisticians are basing their careers on, the missing data field, which is great, but it's still making up the data point. So I think this is a prime example where we have to see that merger between science and statistics. I was asked one time to replace 30% of a data set. That the person came to me and says, I got an analysis that I'd love you to do, and I've got 30% missing, but you know, you can replace that, can't you? I'm like, no, I can't. What, don't you have a missing data algorithm? Yes, I do, but I'm just not doing it. I just don't believe in that. Because if we don't have the data point, we don't have it. And the problem is if you only have a few data points that are missing, what's the point of replacing them? Delete them. So I really see the missing data as a little bit of It's a little bit much when you come from a scientific point of view. And I think we should look for it in research papers to see how much of the data was actually replaced. And another thing is that when we replace missing data, the model usually is going to fit better. So it appeases things statistically, but it's less scientifically aesthetic because it's not a real data point. Most effective, this is my opinion, an ethical strategy is to fit models with versus without outliers, especially if outliers are not errors. Here I'm talking about outliers in terms of, do you delete outliers? What do you do with them? I always tell students if the outlier is an obvious error, get rid of it. But if it's reasonable to say that that outlier was sampled from your population, then you have to incorporate it somehow. And I think that's the best approach, is test your models with and then without the outliers. Is there adequate statistical power to estimate free parameters? Okay. A few notes on power here is power is sometimes a little bit misunderstood because we'll see things like this happen. We'll see a result of p is less than 0.05, but then sometimes we'll wonder, did they have sufficient power to reject that null hypothesis? Well, if you rejected the null hypothesis, you had sufficient power. Power is not an issue. It's when you get high p-values and the authors are saying, I found nothing, that you especially have to say, okay, well, did you even have power to see it? What is power? Well, it's a probability, and it's a probability of rejecting the null hypothesis if it's false. It's a detection. It's single detection. He has lots of power because he has his glasses on. So if HO is false, he's going to be able to see it, and he's going to be able to reject it. If you take the glasses off, HO may very well be false, but you're not going to be able to see it. I use the analogy, put a sign at the back of the class, and I say HO is false, but if I can't see it, I've just wasted all my money on my research because I don't have the power to even reject the false null hypothesis. So how much power should you have? That's the question. What's the ideal for power? Opinions? As close to 1 as possible. We'll never get to 1, but as close to 1 as possible. You want as much power as possible. Too much power is sometimes said in research findings in the literature where it doesn't really make sense to say you have too much power. What's the issue with saying you have too much power? Well, we know the significance test is influenced by sample size. So what happens is sometimes people say, well, if it's influenced by sample size so much, I know how to get it to be not influenced by sample size, decrease the power. We don't want to be hard on the significance test. It's having a hard time doing what it's doing by itself. Let's reduce the sample size. Therefore, we're not artificially inflating it. There's a problem with that. What's the problem? From a scientific point of view, not statistical. Statistical, I guess that makes sense. You reduce your sample size, well, maybe your significance test doesn't come out to be statistically significant. But from a scientific perspective, it kind of violates the whole purpose of science in the first place, which is to obtain the population if you can. So if I look at a whole population here, and I draw the big circle representing the population, and I gather a sample, well, this sample is only going to be a better approximation of the population if I can expand it and get a bigger sample. So this is always better from a scientific point of view. What happens is that as you get a bigger sample, this becomes less reliable as an indicator of any kind of effect. So if you have a very, very high-powered research test, research design, what should you do? Always look to the effect size because it's not going to be inflatable by the sample size. So having too much power is just not right. You want as much power as possible. Now, it's not right statistically, but scientifically, gathering almost the whole population isn't worth it because we have small sample techniques that'll tell you pretty much the same thing about the parameter space without having to look at all of it. So from that point of view, yes, you don't have to collect the whole population. But it should not be from the point of view of appeasing the significance test and reducing sample size. That just makes no sense scientifically. Pragmatically, you can have too much sample size if it's not worth collecting, and a lesser sample size would tell you pretty much the same thing. I just mentioned that. Do not appease a dysfunctional statistical test by lowering sample size or power. Science is about learning about the parameters fundamentally. If you reject the null, you obviously had sufficient power to do so. So power is not an issue if you are rejecting null hypotheses. And insufficient power makes p-values less interpretable. Go to the effect size to get an idea if something happened in the experiment or study. When I interpret a research study, I look at the p-value, but I go right to the effect size because that's the most important thing. Are effect sizes provided, and are they meaningful? Well, I've said that enough that you should interpret both. We look at what they do. There's Cohen's d, and there's an eta squared. Cohen's d isn't inflatable by sample size because in the denominator of Cohen's d, I have a standard deviation, and that standard deviation isn't sitting atop a square root of n. When I calculate a z-test, I've got in that denominator square root of n, so I know that if I can boost my n, that whole standard error is going to decrease. Cohen's d, what does it tell us? Well, we have a mean difference in the numerator relative to an average variation in the population. Sometimes people say, well, this is still a function of n, that the standard deviation is still a function of n, but it's not the same way as in a test statistic like z or t. If I increase the sample size, what happens to the standard deviation? It might go up, it might go down, but it's not necessarily going to increase the value of the d just because you're increasing sample size. So that's the distinction between something like Cohen's d and a z or a t. This one isn't inflatable like the z or the t. And then also eta squared. Another thing, very briefly, were the costs of making a wrong decision against the null incorporated or at least informally considered. I talked about that earlier a little bit, is that if you are to follow the null hypothesis testing quite closely, why are they setting it at 0.05? Maybe it should be set at 0.10. Maybe for another study, it should be set at 0.20. The research literature is kind of obsessed with minimizing the type 1 error rate, but how about the type 2 error rate? That should be considered as well. Are the conclusions drawn consistent with the model employed? I'm going to go a little bit faster because I want to get to my last point. And the sample collected, or does it extrapolate well beyond? So for me, I always look at the conclusion. I look at how well it matches their analysis. Do they run wild in the discussion section, claiming all kinds of things that just doesn't match up with their model and their analysis? If the data do not support the theory, do they say it's bad data? That's kind of like the best, right? It's like, geez, that didn't work. Must be something with the data. Well, maybe it's the theory, right? So maybe you should make sure that you've collected the data in a scientifically rigorous fashion. You make sure that that's good so you can actually test the theory so you don't have to come back and say, that data doesn't know what it's talking about. My theory's right. Otherwise, it leads to ultimate heartbreak where you got my theory just holding the heart together. It's hard to let go because you're in love with the theory. So it takes a lot of contradictory evidence before you can actually change your mind. They say that in in juries, apparently jurors, after they hear the opening statement, make up their mind about the case 60 to 70% of the time or something like that, a high probability of the time. So you think of the actual evidence coming into the trial, it's trying to change that belief point of view. It's kind of similar to maybe a scientist not wanting to let go of their theory. It takes a lot of evidence to change opinion. A priori contrast versus post-hoc comparisons. I think that's another thing to look for in a research study. Did they do contrast? Did they do comparisons, post-hoc comparisons? What's the difference between the two? You'll understand the picture in a second. Well, if you look at these means, serial dating, what could that have? If you look at these means, if I ask you to make a comparison between, say, two means, well, if you don't know what the means are, you're going to have to rely on your scientific and substantive expertise of the problem. If this is an increase in medication dose, such that this group received more medication than this one, you might say, you know what, I think mean 3 is going to be different than mean 1. Therefore, I'm going to do that comparison because it's dictated by theory. What's your type 1 error rate? Well, assuming you set at 0.05, after saying don't set at conventional level, I'm still going to use 0.05. If you set at 0.05, your type 1 error rate is 0.05 for 1 versus 3. Why? Because you're making one comparison. Now, instead, maybe you looked at the data because you didn't know what was going to happen. Well, if you look at the data and you find means of 10, 30, and 32, and I ask you to make one comparison, what comparison are you going to make? You're going to go 10 versus 32 because that's going to have the highest chance of becoming statistically significant. So that's the biggest difference. Let me start with that one. You're going to test that one. But what's the problem? The problem is, how many comparisons did you make here? You didn't make one. Nobody believes it. Nobody believes that you made one comparison. Why? Because you looked at the means, and you went 10, 30, 32, and you said, well, comparing 30 to 32, they're kind of close. Let me compare the most distant means. So you did not make one comparison here like you did here before looking at the data. Once you look at the data, you have no credibility. That's kind of what it means, right? It's like once you look at the data, you're kind of admitting, I'm not sure what I'm going to see. So this is why we use post-hocs in this scenario, where in this scenario we can use contrast without the adjustment, without a Bonferroni adjustment. But when we get here, even if you make the one comparison, you're making more cognitively. So what I like to see in the research paper is even if there's no formal correction, like the Bonferroni or things like that, or some kind of sophisticated post-hoc, I like to see maybe a lower significance level just to kind of acknowledge the fact that they're making more cognitive comparisons than they are the actual empirical comparisons. Let me just skip to the end here. The last thing, number 9, was just about factor analysis a little bit, but we're running out of time. Number 9 is, did the research paper make your jaw drop at least a little? So I like to say that in terms of research papers. I think sometimes we look at research papers and it could leave us with a deflated feeling like, you know, everything seems okay, but I don't know, just doesn't excite me. Like what happened? Was there something there? Why should I be encouraged by the study? Where's the effect? And I think it's important to ask that question overall. How did it leave us? Did it leave us wanting more? Kind of unsatisfied with the research? Was there an impact of the research finding relative to your knowledge of the area? Did it change something? Did it hit you in a certain way? Or is it more than just the same stuff? Was the research likely a type 1 error? How would we know? Well, unfortunately, we don't know because many publishers publish positive-only results. Now, what's this graph? I found this graph online. I figured it would actually make a nice comparison to type 1 error problems. This graph is the total amount of this. It was made in the 1980s, I think, when I guess it's still true today, but back when there's a lot of concern about nuclear war, is that this one dot represents the total amount of firepower combined in World War I and World War II compared to the rest of the dots, which represent the current amount of firepower offered by nuclear bombs. Of course, I looked at that and I figured, hey, that would make a great example for a type 1 error rate. What if the study that you're looking in front of you, that you're reading in the journal, is this one that came out to be positive, that says the medication works, the correlation is there, there's an effect, but what if this is what surrounds it in terms of negative results? The file drawer problem, that all the studies that didn't work because we don't publish them, you never see. So when you do get one that works, that's the one that's published. And the problem is we take that, we say, medication works, I just read it in the study, and we walk around with that knowledge when this is what we might be walking around in. Everywhere around is saying it's not true. So what's the problem with that? Well, here's my own ending little political statement on publication policy. Until all scientific experiences are above water and made available to everyone and scientifically correct, politically correct, in terms of the positives and negatives, so whether you reject the null, whether you don't reject the null, the paper should still be made aware to people. Until we see these as equally valuable, discerning the existence of real phenomena will continue to be a challenge. and science will be used as a tool of social political persuasion rather than as a source of objective truth. Bad experiences are just as valuable as good experiences in discerning the existence or non-existence of phenomena, and both sides of the coin must be made available. This is something I've been really bothered by because we do publish only positive results for a lot of the time. I mean, sometimes there's some negatives in there. But what I think the criteria for publication should be if the study was well performed. So the two criteria, reasonable hypotheses. If the hypotheses don't make any sense, then it's not publishable. And the second thing, has there been good science and verifiable data? Personally, I can't understand that we don't have a verifiable data system where we can check to see what data was used, what's the quality of the data. It's hard to get that information sometimes. Non-criteria for publication, p is less than 0.5 and or large effect sizes. Now, that doesn't mean omit papers that achieve that. It means we shouldn't be looking at papers just because they're statistically significant or have large effects. The science was done right, that result should count so that we can get the relative count of how many positives come out versus negatives. And going back to R.A. Fisher, he basically said the same thing, is that we should be able to account for all research done so that it's immediately available as to the existence of a phenomenon. In the age of the internet, the probability of any theory, probability of H, probability of a hypothesis, should be available to every citizen by a click of a mouse from a politically and scientifically neutral database, so that if you go into the database, you can be made aware that there are the positive ones, but the negatives lurk around. So that you're not influenced by the positive result and walk around thinking that a phenomena is actually there. That's my dog. Thank you very much for attending. I think maybe we have a couple. I have to actually get to a class. So I take maybe a couple questions. Anybody has any? No?
I have always thought it was interesting, even though I understand from a scientific and theoretical standpoint the importance of making hypotheses. I just wanted to know your thoughts. It seems like it automatically lends us to an amount of bias.
Okay, the question is, what's the importance of actually making hypotheses? Or should we maybe just look at the data? Well, one of my favorite examples is if you don't have a hypothesis, the actual result isn't nearly as impressive. So I can make up any kind of narrative around any piece of information, but if I don't have a hypothesis that explains that information, then I'm just not credible. And one example is if I take a ball and I drop the ball and I observe that it fell and I make up a story for why it fell, that's not nearly as impressive as if I say I'm going to take the ball, it's going to drop because of this thing called gravity, and then I drop it. It lends scientific credibility. That's what I'd say. Maybe another question? Yes, close.
Do you have any ideas about that whole positive, negative results in terms of changing the system? Because it's a real serious issue.
It is. The question here is, what are some ideas about changing the positive versus negative results in publication bias? I think it is a serious issue. And the best thing I can think of is that if we all get together and set up that database, where wouldn't it be nice if a citizen, anybody, can click online. So let's take the example of something like climate change. Well, if I look at one research paper, it's going to tell me something. If I look at another one, it's going to tell me another thing. Wouldn't it be nice if I could click on the internet and say, here's the updated probability of the hypothesis of climate change. Tuesday morning, it's at 0.701. New data comes in. For those of you familiar with Bayesian reasoning, new data come in, we update the probability of the hypothesis. So maybe by a year from now, it's up to 0.80. New data come in that conflicted, it goes down to 0.750. It would seem like that would be the way to do it, especially with the ease of the internet. And that would also prevent, if we look at all the political debates going on in politics, statistics being used in a one-shot fashion. Kind of saying, well, I wrote a report that this is the case. Well, people can go Google that online and immediately see where the probability of that hypothesis is online. Great. Thank you again for coming.